Hello and welcome to Physics Online, guys. We're looking today at chapter 2.10, which is Newton's third law. We've now discussed Newton's first, second, and we're going to its third law. So Newton's third law is simply stated as every action has a opposite but equal reaction. Let's quickly go to our textbook and just read there. We call this action-reaction pairs. Okay, a single force cannot exist by itself. Forces always push or pull between two objects. Okay, they'll always occur in pairs. So the key here that we need to know is two objects. Okay, so if we look at a skydiver, a person falling out of the airplane or object falling, the earth pushes that person down, but interestingly enough, the person also pulls the earth upwards. Now, why does the earth not move towards you when you are falling? It's because the earth is much heavier, but every single object when falling is attracting the earth. Okay, so there's two forces. We call this the action-reaction pair. And the key is that it has to be a force on two separate objects. Okay, here we see a runner pushes backwards on the ground, but the ground also pushes forwards on the runner. Okay, so imagine that there's ice and it's slippery. Okay, then even though the runner pushes backwards, the ground or the ice would not be able to push forward and the person would stand still. Okay, here we've seen a nice video of this about how a gun fires backwards and recoils backwards when the bullet goes forwards. Okay, so the first thing that we need to know about Newton's third law is there should be two objects. Okay, and each should exert a force on the other. Okay, so it is two forces acting on each other. Okay, so if I put my hand on the table, now I'm a very good artist, so here's my hand. Okay, let's say it's my foot, or rather, can't draw a nice hand. Okay, so if I push down with my foot on the ground, okay, the ground needs to push up with a similar force. So this is a contact force. Okay, let's say force of foot on ground, or let's make it force of F to G, force to ground, or foot to ground. And then this would be the force of the ground to the foot. Okay, these forces need to be equal. If I step on the ground and the ground cannot give a equal but opposite force back, what's going to happen? It's going to be like you're standing on sinking sand and you're going to sink him. Or if you imagine standing on a piece of paper, if the paper is not strong enough to withhold you, the paper will tear because it doesn't have enough force to resist your weight, your force that you're pushing down with. Okay, so two objects exerting a force on each other. Okay, so if we move forward, it always acts in pairs, but they can't cancel each other out. Okay, forces act in different objects, not on the same object. So it's very, very important that Newton's third law only works if there's two objects. Okay, so if we think of the same principle on one object, and that's why they say, why won't it cancel out? If remember, Charles pushes this way with 100 Newton and Anshu that way with 100 Newton, they will cancel each other. So this is not the same because they're both pushing the same object. But if it's two objects both exerting a force on each other, okay, so imagine here's a very badly drawn person's face, it's very mean, and he gets punched in the face. The fist exerts a force on this person's hand, but the face, on the person's fist, the fist on the face, but the face exerts a force back, equal but opposite. Now, how is that possible? When I break your nose by hitting you in the face, why is my fist not broken? Firstly, sometimes people do break their fists if they don't punch correctly. Secondly, Newton's third law should not be confused although the forces might be equal, okay, there is no way that the result of those forces would be the same. Remember, this is soft tissue, that's a bony structure, so even though the effects of the forces might not be the same, the forces are still opposite but equal. Think of, once again, the picture of the guy jumping out of the aeroplane, okay? He is being pulled by the earth, but the earth is also being pulled by him. Although the forces are equal, the effect is not equal. The earth is not moving to him, but he is moving towards the earth because the earth is much heavier. Okay, so it depends on the properties of the object, how the object responds to this force. But still note that the forces will act on from two different objects on the same object. Okay, so if we look further, Newton's third law of motion says if object A exerts a force on object B, then object B will exert an equal but opposite force on object A. So in other words, another way of stating this is to say that every action has an opposite but equal reaction. Okay, so now guys, if you remember the illustration I had with regards to the balloon, it's very similar to the rocket. So if you have a balloon, okay, and you blow up your balloon, and here is your blown up balloon, and you're holding it there, okay, and you let go of your balloon, what's going to happen? Is the balloon going to stay stationary in the air? So what's happening? The balloon is squeezing the air out. So the air, okay, there's a force, okay, of the balloon on the air. But at the same time, the air is also pushing the balloon forward. Okay, so the balloon is squeezing the air out, but the air is also pushing the balloon forward. And what happens is our balloon flies in opposite weird directions. Okay, so if we now look at something like a rocket, they use the example in the book. Okay, a rocket has two fuel containers, or oxygen and a hydrogen container, and when they come together they form combustion. This is how they use jets and rockets. They use oxygen and hydrogen to form, to combust, and that forms heat and water. So if we want the rocket to accelerate, we can use the acceleration while it's still in this atmosphere. But the moment it gets out of the atmosphere, there is no air to push against the rocket. So now the rocket is in a state of, let's say, Newton's first law. Okay, my rocket is now moving at a constant velocity, let's say of 100 meters per second. Okay, times with 3.6, that is 360 kilometers per hour. Quite quick. Okay, so now I want my rocket to go further, but it's in space. Okay, so what they do sometimes is they detach the fuel tanks, because we've used up all the fuel, from the rest of the rocket. Okay, now the same force that pushes this backward is going to push that forward. Those two detaching, or a little explosion there, is going to make this capsule go faster, and the fuel tanks are going to go backwards. And what we'll see is that when the fuel tank detaches, it will go quicker. Let's say, for example, 120 meters per second. Okay, so they use this rule that when things explode away from each other, the forces are also equal but in opposite directions, and that will make the smaller object go faster, and because it is much lighter, it will even accelerate faster than this one and reach a higher speed. Okay, so back to our textbook. They also use rockets like the balloon, how we let go of the balloon, and then they explain a little bit here of the jet engine, how the air, the heat pushes back, okay, and then the front pushes forward. So there's a whole thing there of action reaction forces. There's many other examples that you can look at as well. So here we see two trolleys. there's a spring between them connected there. If you hit the spring shoots both of them in opposite direction. Another example of this could be like when a person is in a boat, okay, on the river, and he wants to climb off on the jetty. Okay, so when I'm standing here, I'm on the boat. When I apply a force this way, I'm applying a force on the boat with my foot in this way. I want to move that way, but the boat will apply an opposite but equal force. And what often happens is that the boat moves away and the people fall into the water, okay? Because opposite but equal forces being acted on. Just moving your foot backwards on the boat, okay, in order to move forward will make the boat move backwards, okay? Similar thing can happen when we have two people, okay, standing hand in hand, okay, hand against hand on the ice. So if you're wearing skates and you're pushing away from each other, so both of them are pushing away with the same force, even just one can push, and they both would move backwards depending on which one is heavier. One force, let's just say he pushes her, there's no way that he won't be affected when he pushes her, so both of them will be affected with a force opposite but equal. Now a good example, guys, even if I rub my one hand against my other hand, okay, both forces feel that, okay, when I slap, okay, both hands feel a sting. Okay, so there's no way that I can slap you without me feeling it. Okay, both forces are acting in opposite but equal directions. Okay, so guys, that is basically Newton's third law, and we'll look at some applications to that. But I hope you have an awesome day, and yeah, please let me know if you don't understand anything. Have a nice day. Goodbye.